So welcome everyone to our weekly Astro seminar. It's a great honor and delight to host here, even if remotely, my own PhD advisor of old, Professor Barak Kol from the Hebrew University. Barak did his undergrad at Tel Aviv University, then a PhD in Stanford with Lenny Susskind, followed by 2 postdocs in Tel Aviv University and Princeton. Has been a faculty member at the Hebrew University for almost 20 years now, during which I had the pleasure of taking several of his courses and, of course, advisorship for PhD. And it's great to have him here today with us to talk about a very old and still interesting problem, the free-body problem. Barak?
Thank you, Ofek. Thank you for the invitation and the kind introduction. Please feel free to connect your cameras. It helps me to, if I can see people in front of me, and please feel free to ask questions as we go along. The title of the talk is The Flux-based Statistical Prediction of Three-Body Outcomes. So it's a talk on the three-body problem. I will soon describe the problem, but what I'm going to tell you is first why this is such a long-standing puzzle, rather deep and fruitful along the history, where a lot of science branches grew out of it, and how it was possible recently to provide an exact reduction of some sort of solution of it, and to obtain a leap in accuracy with simulations, with numerical simulations. So to date, this is the most accurate the most accurate available prediction for certain quantities. Okay, so it's based on, the talk will be based on this paper that was recently published in Celestial Mechanics and Dynamical Astronomy, actually the beginning of this month, and a more recent archive paper which compares the theoretical predictions against numerical simulations, an international team with Manwadkar, Trani, and Lee. And our outline is going to be, we'll define the problem, and we'll describe its history in order to appreciate more its depth and to, and then we'll describe just the main results, some comparison with simulations, and a little bit of derivation, not much, and end with a discussion. So, what is the problem? The problem is very simple. We have 3-point particles, 3 masses, m1, m2, m3, and it is moving under the influence of mutual Newtonian gravitational forces. So just the simple formula F equals to G m1, m2 divided by R12. Oh, it should be squared here, of course. So the square is missing, but I won't be able to fix it right now. And the goal would be, given initial conditions, all the positions and the velocities, we would like to predict the long-term motion of this system. Okay, so it's extremely simple to define the problem, but as we shall see, the solution is not simple. Astrophysically, these 3-point particles could be 3 stars, but they could also be 1 star and 2 planets, or a star-planet moon, or 2 stars and 1 planet. And of course, the star could be replaced by some other forms, such as neutron stars, black holes. But this doesn't matter for the within the idealization as point particles. So in order to understand what's going on, I'll show you one of the simulations. Oops. Okay, so I think you can see the simulation, right? Okay, so now look at this and see how random the motion appears to be. See, each time we have close encounters. By the way, the time is not real time, but it is some kind of rescale time. There is a close encounter between two, and then the spectator meets one of the two. You see? And it goes on for quite a while. This is a simulation performed by Alessandro Trani from Japan right now. And this goes on for a while until one of the close encounters is strong enough to throw out one of them. Here, you see, it was thrown out, but not very far this time. It returned. I can let it go faster. Maybe even faster. It goes on for a very long time. You see that it's very random, very unpredictable. Oops, and here it flew out. But this time it's below the escape velocity. Here again, it's below the escape velocity, and the binary and the single one that's separated will eventually turn back. This is almost equal masses, by the way, slightly unequal masses. And the point particle is just a point. The tail is just to show you its recent history. Okay, so one will have a sequence of such ejections. They are known. We see that the ejection can end in a sub-escape, so below the escape velocity, but one of them finally will reach escape, and escape is irreversible. Here is the escape, hop. The yellow one is thrown out above the escape velocity, and that's the end of the story. From now on, it's a very simple motion. The yellow one runs to our left, and the binary moves as a two-body motion to the right. Okay. Any question about this motion, which is rather typical? Okay, so I proceed. So now I'd like to tell you a brief history, because this problem has a history since Newton and Principia. So Newton was successful in explaining the motion of the planets, of Earth and all other planets around the sun. And then he wanted to explain the motion of the moon. Now, to lowest order, the moon orbits the Earth in a Keplerian orbit. But there are important corrections to it, some precession effects that were known already to the ancients. And Newton tried to understand it. It's in his book, The Principia. He tried to understand it by the influence of the sun. Okay, so the Earth is the leading effect. It causes it to move in an ellipse around the Earth. But then the sun provides a correction, and it makes it into a three-body problem. Actually, it's a hierarchical three-body problem, because the size of the binary, the size of the Earth-Moon system, is much smaller than the distance of this system to the sun. Okay, so it's a hierarchical, there is a distance hierarchy. In fact, in this case, there's also a mass hierarchy, but what is more important is the distance hierarchy. And because of the distance hierarchy, one can compute corrections to the motion, and that's what Newton did. He was able to get qualitative the needed effect, but quantitatively, he could explain only half of the effect. Okay, and that's as far as Newton could get there. But his followers, and that was in the 1740s, Clairaut, D'Alembert, the Frenchman, and Euler, they tried to explain the motion of the moon. At first, they thought it would be impossible to explain, and they declared a deviation from Newton's law of gravity. So they modified, I don't know if you can see my cursor, but they declared the modification to Newton's law of gravity, adding a 1/r correction. But within a year or two, Clairaut found that actually there was another correction, another perturbative effect, that once he added it to the one that was known to Newton, was able to explain this precession of the moon, of the orbit of the moon. And there was no need to change Newton's law, fortunately. So that was a very hot scientific debate of the time. Now the years go on, and Euler gets interested in going beyond the hierarchical systems, in finding exact solutions to not non-hierarchical setups. And the mass being non-hierarchical, the distances being non-hierarchical. And he's able to find the following solutions where all masses are collinear. So they all lie on the same line, and they are rotating in the plane. So this requires very special initial conditions, but these are exact solutions. Okay? And they found them 1767. A bit later, our friend Lagrange found the equilateral solutions. Again, if the masses are equal, it is rather clear that an equilateral moving with some angular velocity is a solution. But even if the masses are unequal, this is special to gravity and the fact that the inertial mass is equal to the gravitational mass, this continues to be an exact solution to the three-body equations of motion. By the way, for Lagrange, this is a side effect. He submits a paper to a prize contest of the French Academy of Sciences, and his starting point is very different. He's suggesting novel variables, not the usual variables that we use, but instead the edge sizes of the triangle. He takes them to be the variables, and then he needs also to use some additional geometric variables. So not the vectors with respect to some origin, but the distances between the stars are his variables. That allows him to reduce the order of the system of differential equations. And as a byproduct, he's also able to find this exact solution. These two solutions might be familiar to you from the Lagrange points for a satellite moving around, let's say, the Earth-Sun system or the Jupiter-Sun system. So they are just the special case they are just a special case of general masses of the solutions of Euler and Lagrange. We continue. And with time, since no one was able to find any more general exact solutions. Well, general for general masses, I mean, not general initial conditions. So people turned into perturbation theory. And when you study the motion of two planets around the sun, Lagrange and Poisson invented the Poisson bracket for the purpose of the three-body problem. And later, Carl Gustav Jacobi got interested in this problem and contributed the Jacobi invariant and also and one additional reduction of the equations of motion relative to Lagrange. So there were interesting progress in perturbation theory, but we don't need it. So I'll just proceed. Now comes Poincaré, and this is really the watershed moment of this story. There was a prize offered by King Oscar of Sweden and Norway for mathematical advancement, and one of the problems that was available was the three-body problem. And he applied qualitative methods for differential equations, which he studied beforehand, to study the circular reduced three-body problem. By reduce, it means that one of the bodies is much lighter than the other two, and also circular. So it means that the two are moving, the heavy ones are moving in a circle, and the third light one is moving in their background. And after a rather long development, he arrived at the conclusion that this problem exhibits a very interesting phenomenon, a sensitivity to initial conditions. This means that even if you change the initial conditions by very little, after some time, after some typical time, the changes between the original trajectory and the perturbed trajectory become large. In other words, the deviation between the reference trajectory and the new trajectory grows exponentially in time with some typical time. So that practically limits our ability to predict, because we never know the initial conditions with absolute certainty. Therefore, after several typical times, we lose all predictability. And this is the phenomenon that is today known as chaos and is one of the bases of nonlinear science. And it was discovered by Poincaré in the setup of the three-body problem. He also invented Poincaré section, Poincaré recurrences, if you've heard of them. He also invented topology, so homology and homotopy. So modern topology was invented by Poincaré around the same time, and he cites as one of his backgrounds or motivations his work on celestial mechanics and the three-body problem. He's able to prove that there are no additional conserved quantities beyond the universal ones: energy, linear momentum, and angular momentum. And all of this causes him to conclude that the problem does not have a deterministic solution or a closed form mathematical solution. Okay, so this is really, okay, let's see. Let me just follow what I have here. So he won the prize. He wrote a book, Les méthodes nouvelles de la mécanique céleste, New Methods in Celestial Mechanics, his three-volume masterpiece as a result of this research. And finally, he arrived at the belief that there is no analytic solution in closed form. However, I should say that around 1910, the Finnish mathematician Sundman showed that a series could be given, an infinite series could describe a convergent infinite series could be given that is a solution. Okay, but it's unuseful. You need an exponential number of terms just to get a typical time, and after the typical time, after like half a revolution or something like that, after that typical time, it just it's impossible to, it's completely impractical, this power series. Okay, so we have here a paradigm shift. It's not anymore the clockwork universe where if you know the forces and if you know the initial conditions, then you are able to predict the future because of this extreme sensitivity to initial conditions. Then the story is very different and we lose predictability. So I have here loss of determinism, and you may just think, people thought at the time that it just becomes an unsolvable problem. And then you turn on to other problems. So relativity was invented, quantum mechanics was invented, and it was not considered anymore at the forefront of science as it has been for the first 200 years, but still many people continued to work on it. So until that time, I only reviewed some of the people that work on it, but others include Laplace and Gauss. And after that time, or Poincaré, contemporary was George Hill from the United States, of the Hill radius. And then in the 20th century, the famous Levi-Civita and Georges Lemaitre, they also worked on it, but I'm just mentioning this, we won't need it. And the next step in our story, after we passed this watershed moment and we understood that a deterministic solution that was sought for 2 centuries is in fact impossible, then computers arrive. And once they arrive, we can do computerized simulations. The first simulations were done by Agekian and Anosova in the Soviet Union in 1967. And afterward, Valtonen started contributing, a Finnish physicist who has written 2 very good books for the popular public and for physicists and reviews. He's been working on it for decades. And one of the main results for us is that if the total energy, kinetic plus potential, is negative, and of course it is conserved, then the system cannot disintegrate into 3 free particles, because 3 free particles always have positive energy. They have only kinetic energy if we have 3 guys flying out. But it can decay into 2 plus 1. So negative energy can decay to a binary flying away from a single. And there is no conserved quantity or anything to prevent it. And in fact, that's the generic case. So whenever we have a chaotic motion, a non-hierarchical motion, which is generically chaotic, it will finally disintegrate. In chaos, we have the same rule as in quantum physics. Anything allowed to happen will happen, okay? And now the question becomes more clear. Given initial conditions, what will be this final state of disintegration? Which one of the 3 will be the one to escape, to so-called escape, and in which direction, with what velocity, what are going to be the orbit parameters of the remaining binary, okay? So these are the questions. And then the question is, can we have any theory for it, given how random the problem is? So to see the next breakthrough, you can imagine throwing a die, קוביית משחק. So for this case, we know all the physics. We know the physics of gravity, we know the physics of bouncing off the table, but we know that it's practically impossible to predict how the die will land. Now, if it's an uneven die, an unfair die, we can say that it has more chance of ending on one of the faces. Or if it's a fair die, it's not as interesting. It will be equal probabilities, 1/6 for each side. So then you say, aha, when the problem is very random and you cannot have a deterministic prediction, what about a statistical prediction? Okay. So all along we were asking the wrong question. It was the wrong question to ask for deterministic. Yes, in a moment I'll take your question. Thank you. It was wrong to ask for all along for a deterministic solution. This is impractical because of chaos and sensitivity to initial conditions, but it should be very practical to provide a statistical solution. Given the initial conditions, what is the probability distribution for different outcomes? Yes, please.
Yes. Can you use, in the case of non-equal masses, can you use this argument of conservation of energy and the ergodic argument essentially to argue what would be the probability of any of the 2 particles or stars to get out as a doublet and one as a singlet?
This is exactly the question now. This is exactly the question. Thank you. Yes. So we know that we start with some initial condition when they're all in 3-body, non-hierarchical 3-body motion. If the masses are equal, of course, there is no difference between them. So just by symmetry, it's clear that the statistical prediction should be third, third, third. And as I will show you, simulations prove that correct. And now the question is, what happens if they're non-equal? Can we predict which one has a higher chance of escaping, and maybe the other outcome parameters, the directions, the eccentricity of the binary, and so on, okay? So let's see what was done in that respect. So now we enter the statistical theory, which is the subject also of the present work. That was suggested first by Monahan in 1976. It is not the statistical mechanics of a lot of of a huge ensemble of bodies or a huge ensemble of a huge number of molecules, like in a gas thermodynamics, but it's rather the statistical mechanics approach of Gibbs, where even for a system with few degrees of freedom, because it is ergodic and because its motion is very random, you apply statistical tools. And the basic tool, as we know, is to equate probability with phase space volume, because phase space volume is conserved according to Liouville's theorem, and that's the basic postulate of statistical mechanics. And now you say, given the conserved charges, can we compute the phase space volume that is associated with the different kinds of disintegrations of the system? Can we compute this? And there are some challenges here. So it's a chaotic system, but it's a chaotic system which disintegrates. So it moves only for a finite time, and then it breaks down. And it is unbounded. So you can expect the phase space volumes to be infinite. So then you have a problem of infinite probabilities. And finally, we have there both chaotic motion and regular motion. Both, the system can exhibit both of them depending on whether it's hierarchical or non-hierarchical. So actually the phase space is really mixed in a very bad way, maybe in a fractal way, between a chaotic part and a regular part. Okay, so all of this makes it challenging to compute these phase space volumes. And the solution that was chosen from the early days of the statistical theory is to introduce the so-called strong interaction region, denoted by capital R. What is this strong interaction region? That's important because that's the point that we're going to improve over. So they say we're going to assume that they separate when the binary and the third guy are at a distance RF. F stands for the effective system, that is a binary and third guy, when the distance is smaller than this capital R. Okay, so in this way, we consider only systems with finite size, and then also finite phase space, and then also finite probabilities. So we avoid the infinite probabilities, and we also avoid in this way motions which never go through a chaotic phase. So motions where you have a binary and the third guy is coming along and it goes very far from the binary and just passes to the other side. So these are motions that are they're never compact enough. And by requiring that the system at some point is small enough, we can get rid of these motions, which we don't want as part of our disintegration out of chaotic motion.
Can yes. I ask, I have two questions regarding what you said. One, yes. Is in nature, the systems are really unbounded? Because I can easily imagine a system, let's say of stars, that when they interact, there is some friction because of stellar wind of some kind, which will turn an initially unbounded system into a bounded system. And the second question related to this current slide, where you define a strong interaction region or typical radius, capital R, but this should depend also on the momentum that you have. It's not independent on the relative momentum of the objects.
Good. So what I said, when I said that the system is unbound, I didn't mean that it was unbound energetically. I meant that there was no allowed size. It could have any size. And indeed, if you remember the movie that I showed, the video that I showed in the beginning, there were these sub-escape excursions where a binary separates from a single and they fly out, and they can fly out to arbitrarily large distances, but then they can also fall back if their velocity is below the escape velocity, or they can fly out, okay? So there's nothing that limits the size of it in the problem as defined, Of course, if you add some additional factors, you can change that. But let us first understand the simplest problem, the problem of just gravity. And in this case, because the gravitational force has an infinite distance, then there is no natural box in which the whole evolution takes place. Okay, but it's true that there is some that R is related to the conserved charges. So if you know, so the way they fix R, for instance, is once they see the size of the binary that was emitted, then they'll say, okay, let us require that this R is just a few times the size of the binary. Okay, so you have some typical scales, and you can, it's not completely arbitrary, the size of R. You have some guidelines how to choose it. However, there is still something arbitrary about it, because this strong interaction region is not really part of the input of the problem. It is something that you put in by hand. It's not part of the initial conditions, you see? So there is something artificial or arbitrary about it, even if the scale of it is motivated. But the exact value, there is something arbitrary about it. Okay? So
could you make the cut instead of an arbitrary fixed R? Make the R dependent on the, I mean, it's phase-based, on the momentum of the body that's going out compared to the other pair, because then you have the actual escape velocity. You could calculate the escape velocity for body 3 relative to 1 and 2 when they're close together, and that will give you a physically meaningful R.
So I can discuss this more in a question session and open a page, but right now I'll just repeat that it indeed R is chosen in some way like this, not proportional to the momentum, but proportional to the binary size. So if you have a certain binary size, then you say that's roughly the size of the system, and we require that R is maybe 2 times the binary size. Okay, so something like that. So it goes in the same spirit of what you and Asaf suggested of making a physical order of magnitude for capital R, but there is no sharp value that is dictated. Okay, but you are right that within this order of magnitude, one can obtain rather meaningful calculations. And I'll tell you that the next step that I want to tell you about is a very recent paper, just from, it appeared just two years ago by Stone and Lee. Nick Stone is an astrophysicist from the Hebrew University, and Yulia Wright one. And Nathan Lee is from the University of Concepcion in Chile. And they were able to carry this program that was initiated in '76 to a very high level, in which they were able to evaluate these phase volumes in closed form. And they were able to avoid all kinds of approximations that were done before, like assuming the motion is planar. So it was too difficult to compute initially. So people assumed that all 3 bodies are always planar. Or they said, let's forget of conservation of angular momentum. Let's just take into account conservation of energy and linear momentum. So they avoided all the unnecessary conditions, and they were able to compute sigma in closed form. They still used the same assumption, the same framework. So they still use the strong interaction radius. And technically, they use something known as the Delaunay variables. And this was all over the press. And this is how I heard of it. So it was published maybe in December, a year and a half ago. And I got very interested in it. I taught analytical mechanics several years earlier, and I knew a bit about this problem, and I could appreciate that it's a very important problem. And I sat down with Nick Stone and he explained it to me, but then he also pointed out to me this R. He called it even a fudge factor. okay? So I realized that this is not a complete solution, because if you have in the solution a parameter which is not part of the data of the problem, not part of the input, then it's not in any sense a complete solution. So why is it important, this problem? So I think given all this history, it's partly clear. Yes, perturbation theory, a lot of perturbation theory was invented for this problem. Modern topology was invented, grew up in a part at least from this problem. Chaos was first encountered from this problem. It's very simple to define, so it's very natural to be interested in it. It's also a prototype for chaotic systems. So if you want to understand chaotic systems, it's a good place to start. And there are also numerous astrophysical applications. For one, the origin of the tight binaries that we detect with LIGO and other gravitational wave observatories is currently a puzzle. How could they become so tight within the age of the universe? And one of the suggested solutions is through three-body interactions. Another interesting astrophysical question is the dynamics of star clusters, regions of space where there are hundreds or thousands of stars which are relatively close, and then you have many binaries, and three-body interactions are quite common. And then if you want to understand the dynamics of this cluster, then you want to understand three-body interactions. Okay, so I think I mentioned a bit already my road to the problem. I was working throughout my career always on fundamental physics, but usually on rather different problems. I was working on high energy physics or quantum field theory, and I was working on Einstein's gravity, GR. But I wasn't working in astrophysics and on this problem, and I just got to it somewhat by chance. But when I saw this thing, I thought to myself, just a minute, there should be a more complete solution, and maybe even I can find it. And given its central place in the history of physics, it could be worthwhile. So I started working on it quite obsessively. And then there was also the first lockdown, as you remember, in March and April. And from that grew out the paper. It took several steps, and one discovery followed another. And in the end, I got to the following results. So I'll just try to describe now the main results. We're going to change we're going to change the foundations of the statistical theory, and we're going to get a leap in accuracy, okay? So I re-examined the very foundations of the theory, and the foundation, as you remember, like any statistical theory, was that probability is proportional to phase volume. Instead, since the problem is not closed, but it's open and there is disintegration, I replaced phase space volume by phase volume flux. So we can think of phase space and we can think of the flux of trajectories flying out to infinity. So this is really what we should be looking at. And we are computing in this way, in fact, not probabilities, but decay rates. So probabilities per unit time for the system to decay into any of the possible end states. I'm going to show you now an exact reduction of this decay rate. So I will not show you the decay rate itself, but I will simplify it to the determination of a somewhat simpler function that is called the emissivity function, and I will get there in a moment. So let me show you. So let's briefly set up and state some notation. So here is our Hamiltonian for the three-body system, simply three kinetic terms and three mutual Newtonian gravitational terms. And the conserved quantities are the energy, the angular momentum, and the linear momentum. And in order to understand the outcome parameters, we have to understand, to look more carefully at what happens when the system disintegrates. It divides into a binary and the third guy. So one kind of parameters are the parameters of the binary. So we have the energy, the total energy of the binary, L, the total angular momentum of the binary, and the perihelion angle, or if you like, the Laplace-Runge length vector, which points at the perihelion. Okay, so these are the parameters which parameterize the binary. And then we have similar parameters which parameterize the effective system, where we replace the binary by a point. So we replace the binary by a mass which is the sum of the masses of the binary at the location which is the center of mass of the binary. I call this the effective system because now it's a two-body system where the binary is replaced by a point particle. And now we have an energy of the effective system, an angular momentum of the effective system. It just flies out. Far away, it is just linear motion. Closer by, it's a hyperbolic motion because you still feel the gravity between the single and the binary. And there's also here a perihelion angle. These quantities, I don't know, there are 5 and 5, so maybe 10 quantities, are constrained by the total conservation laws. So the energy of the binary plus the energy of the effective motion have to equal to the total energy. So we see it here on this illustration. And same for the angular momentum. The binary angular momentum is a vector plus the effective angular momentum of the relative motion have to sum up to the total angular momentum. And here also I have a graph showing the binary energy and the magnitude of binary angular momentum. They can just have all kinds of values that are limited to some sub-range. Oops, it's jumping out of its own wheel recently. So they are constrained by this inequality that the energy times angular momentum squared have to be smaller than something that we can call the binary constant. It's just a two-body problem here. And it's an interesting constant. It will show up later, so I want to define it. It has here the reduced mass, and it has the alpha, or GM1, M2 of the two bodies squared. Okay, so this combination, reduced mass times potential strength squared, I call the binary constant, and it will show up in a moment. So these are the things that we want to predict their distribution. What will be the distribution of epsilon or epsilon f? Their sum has to be the total energy, but the energy of the binary, what will be the angular momentum of the binary, and so on.
I have just a quick question. Is there a possible outcome in which there will not be a binary, but the three stars will just move away as three independent, or this does not exist?
Good. So a triple disintegration is possible only if the total energy is positive.
Right.
That's because a triple disintegration has only kinetic energy and no potential energy. So it's possible, but we are interested in the case of negative total energy. And in this case, it is impossible. Okay? So that's definitely important for other kinds of motion, but those kinds of motion are not as chaotic and ergodic, and they have a somewhat different nature, so we're not looking at them right now. Well, we have here some kind of schematic depiction of phase space. So phase space we have 9 degrees of freedom. We have 18 dimensions of phase space. I cannot draw right now this 18-dimensional space, but I can have a schematic form of it in a form of kind of a piping diagrams, like in plumbing. And basically, the point is the system is depicted by a single point, as always in phase space, and it moves here. And we see that we have several regions. We have the ergodic container, where it moves for a very long time. And then every once in a while, it gets out and it goes to this mixer. This is these ejections that we saw, where it separates into 2+1. And there are two kinds of ejections. Either it goes to an escape, and that's the end of the story, or it goes to a sub-escape, where the 2 and 1 fly out, but then they're below the escape velocity and they fall back. So the point moves here, falls back to the mixer, and then it can go back into ergodic motion. Or there could be something that we call regular motion, for instance, flyby or exchange, something very fast, and return back to the mixer. Okay, so this really shows you all the possibilities for the motion within this diagram. And we built a system of equations to describe the statistical evolution of the system. So for instance, PE is the probability that the system is in the ergodic container. So maybe we start with initial conditions where the system is there with probability 1, but then over time, it spills over to the other places. So we have here the outflux G out, and we have an influx back G in, and we wrote some system of equations for it. And in this system of equation, an important place is taken by the decay rate, gamma. So that's the rate at which systems go out of the ergodic container and spill out to either the escape or the sub-escape trajectories. So this is what I'd like to focus on, this decay rate. And for this decay rate, we have the prediction, a clear prediction, or a clear reduction, better to say. And here it is. So it's a rather simple formula for the differential decay rate. That's for differential ranges of the outcome parameters, the binary energy, the binary angular momentum, the relative or effective angular momentum, the two perihelion angles. We have here this K, the binary constant that I told you to try and pay attention beforehand. And we have here one unknown function, epsilon of u, or the emissivity. So here is K, I already defined it, the binary constant. And what is this emissivity? Emissivity is so far an unknown function of the outcome parameters, but it can be measured independently. And it's a bit like emissivity of a black body. So this is what we call a gray body. A black body is a case where the emissivity or the absorptivity is 1. And in analogy with the physics of black bodies, here we define the emissivity as the chance of, out of all the trajectories that are coming out, how many of them came from chaotic motion. Conversely, we can define the emissivity through an absorptivity. So we reverse time, we take the 2+1 system, and we reverse time, and then it starts falling back. And then we play with all possible chaotic angles or chaotic, it's called true anomaly, I think. So the place of the binary in its motion, and we compute what is the probability for this to evolve into chaotic motion once we throw it in. So some initial conditions will end in chaotic, some in non-chaotic, and that's the issue here.
Can I ask?
Yes, please.
Can you give an intuitive explanation of what the phis are doing there?
Yes. So the d-phis, these are the perihelion angles, and you see that the distribution is independent of them. So it just runs, so it's just a uniform distribution over the perihelion angle of the binary. So if you rotate the binary, the initial state of the binary, it doesn't affect the outcome.
So
Sorry, not the initial state, but the final, the outgoing binary, different binaries with same parameters but different perihelions all have the same probability of being ejected at this level. But there's also the story of the emissivity. So the emissivity could change this. So there is the explicit factor and then the emissivity. The explicit factor does not depend on the perihelion angle of the outgoing binary. Okay, it's uniform in it.
If Ks depends on Ma and Mb, you actually have three masses. Do you need to consider the three parallel channels and
exactly? Exactly so. So this is the differential decay rate for given S, where S is the escaper. It's 1, 2, or 3. Okay, so S is one of the outcome parameter. It's a discrete outcome parameter. Which one escaped? Body 1, body 2, or body 3. And then we also have the continuous parameters, the angle at which it flies out, the energy, and so on. Very good. So now we're going to compare this with some numerical simulations. But we have a problem. We have a problem that we still have here an unknown function, which is still under study. But in some cases, we can kind of, the results are independent of this emissivity, or the emissivity averages out. And the most interesting quantity is the quantity of the escape probability. Which one of the bodies escapes? Okay, so first it's interesting to guess which one of the three bodies has a higher probability to escape if they have non-equal masses. Okay. That's interesting. So it can only depend on the mass. So what would we think? Would it be the lighter mass that has a higher probability to escape, or the heavier mass? So we have this sequence of close encounters, and then one of them will be strong enough to knock out one of the three, and it will fly away, and the lighter one has the higher probability of being knocked out. So it is true, this intuition is correct. The lighter body has a higher probability, but all of them have some probability of escaping. And we're going to make two assumptions. One of them is the ergodic assumption, so that the system is very chaotic, very mixing, and it explores all of phase space. Equivalently, the ergodic assumption could be stated as loss of memory, so the final result is independent of initial conditions. And we're going to assume also that the emissivity averages out for these escape probabilities. And now I want to show you the main results that appeared in the paper from this January, from the recent January. And you see here different systems. This is an equal mass system. For the equal mass system, you see here the probabilities of ejection, roughly third, third, third. Even though the initial conditions are not symmetrical, I should say. The initial conditions are a binary in circular motion, and the third guy at rest far away, at rest far away. And then we let it fall in, and then the three-body motion starts, and then one of them finally gets ejected, and we record which one of them it is, and you see that the three numbers corresponding to the three bodies are rather equal, and you see that the theory also gives, of course, because of symmetry, equal probability. We compare it here to several other theories. I will mention Stone and Lee that we already mentioned, and the theory in the book in the review book by Valtonen. So here everybody has this equal probabilities. But now let's look at unequal masses. Then we see that the lightest mass has a higher probability of 57%. The medium one has 27%, and the lowest one has 16%. Look at the predictions of this theory. It's at the 1% level precise. If you compare it to all the other theories, they're in the general direction, but not as precise at all. And even if as you increase the inequality of the masses, you can see, let's see here, 10, 15, 20, the masses in some units. The 10, the lightest one, has was measured to have 78% chance of being emitted after 1 million simulations, I should say. And the theory was exactly the same. Here, there's something suspicious. Even I don't know if it's a mistake here, because here it appears as if it's too close. So let's look at the 10-20-20 here. You see that 87, almost 88%, and here 88%. And the two light ones have almost equal probabilities, which is around 6%. So you see that it's very close. Okay, so this is this leap in accuracy in computing the ejection probabilities. And that's why this is the most accurate statistical theory to date, at least for this quantity. By the way, the formula that we use to compute the theoretical values is very simple. It is just Ks to the 3/2. This is for this domain of variables. There is some condition within some domain of variables. The unnormalized probabilities are very simple. There are 3 binary constants because there are 3 possible binaries. And you just take this binary constant to power 3/2. And this gives you very simple formula for the unnormalized probabilities. So now I'm very close to ending. So I've shown you how we changed the foundations going from computing phase-space volumes to computing fluxes. We don't have anymore the strong interaction radius. Fluxes are finite, even if you compute them far away. In fact, it doesn't matter where you compute them. So we avoid the infinite probabilities in this way. But we have another problem that the normalization factor appears to be infinite. That's the total phase volume, and we need to regularize it. And we also took care of that. That will be in a future publication. We're going to estimate the decay time. All previous works tried to fit the outcome distribution, but they didn't ask how long would it take to decay. Our theory also allows to study or predict how long would the decay take. So I will skip the main ideas in the derivation, and I already mentioned them as I went, I think, but there was this leaky container idea, that there is a closed container with a small hole in phase space, and then the probability to escape was the size of the hole divided by the size of the container. And we also incorporated this idea of absorptivity equals emissivity, which comes from Kirchhoff's law of thermal radiation, also related to gray body radiation. Or
I have another question about this decay time. So when you're essentially when you're using this ergodic approximation, it means you should be unsensitive to the initial conditions.
Right.
Right. So that's why the 1/3, 1/3, 1/3 is not surprised, because you don't care what the initial conditions are. But when you're calculating the decay time, then you must add the time that it takes the initial condition to relax, which under certain conditions could be non-negligible, I would assume. I don't know.
Right. So you have to define this decay time properly. You're absolutely right. And we define it as the decay time from a starting point, which is ergodic. So I don't start at hour t equals to 0 when the third body is at rest. I have to count it when it starts moving in 3-body motion, right? And then this I can take as my beginning of time and ask how long would it take since that moment until the decay. Since you mentioned it, I will also want to stress that the ergodic approximation holds rather well. Here we go, sorry. So again, if we look at the equal mass case and we look at the measured probabilities, you see how equal they are, even though the initial conditions were very non-symmetrical. There was a circular binary and a third guy at rest. So you may think that the third guy's chances to get emitted are different than the other two. But because it gets absorbed into this random ergodic motion, it really forgets which one was outside and which was inside the binary. Now they're all equal, they all have the same mass. And the simulations demonstrated that the ergodic assumption holds to a good approximation because these probabilities are really all very close to each other. So I just wanted to stress more this point following your question. So I've explained why I call it the flux-based theory because it really has a different foundation. I've explained that we obtained not an approximation. All other approaches got to a very good fit with the data. So that's the paper of Stone and Lee, and more recently, a paper from the Technion by Chagai Peretz and Yonadav or Barry. Barry Ginat, yes, he's a graduate student. So very interesting paper, but these are all, you can consider them to be approximations, or if you like, some approximations for the emissivity, because they give very specific predictions. So we don't do that, but we make a reduction. We say it is some known function times an unknown function, and the unknown function, all we know about it is that it's bounded. It's between 0 and 1, this emissivity or absorptivity. There is no spurious parameter. So R was eliminated from the story. We get the decay time statistic, as I mentioned, not only the outcome statistics, but also the decay time statistic. And we have a leap, a dramatic improvement in agreement with simulations. Okay? So I'm sorry if I went a bit over time, but I think we're roughly on time. And I thank you for your attention. And if you have any questions, you're very welcome. Oh, the problem has been cracked, okay? And we have a solid foundation for statistical theory. And okay, now I can thank you.
Thank you, Barak. I have a few questions, but first, if any of the students have any questions.
Yes, please.
So, okay, first of all, just a comment I saw on your results page. 1% was about the error in the statistical probability distribution, the empirical one. That
yes,
is, if you
1
have,
absolute percent, I call it.
What?
Yes, please go ahead.
So if you have 1% as an experimental error, it seems that the theoretical prediction actually fits within the experimental error bound. So that could mean that you're perfectly correct. It could mean that if you reduce the experimental error by another factor of 10, you'd start finding discrepancies in the theory.
Okay, so let's look again at the table. I think I understand the question. So I will reshare screen. We go to the transparency of the, here we go. So
look at the equal mass case, the first one.
So the simulations here don't really give the error. It's not so easy to estimate, but let's say since we have 1 million simulations, then we can expect the less digit, the per mil digit to be the digit of accuracy, okay?
No, we have a better estimate, right? For the equal mass system, we know the correct answer should be 1/3, 1/3, 1/3.
That's well, maybe if you assume the ergodic assumption, but in reality, the ergodic assumption doesn't have to hold perfectly, okay? So
yes, but
there could be a difference between the one that started far away, but I agree this could be a measure of another measure of the error, okay?
At least the theory assumes the ergodic assumption, so you can't expect the theory to do any better than how well the experimental data satisfies the ergodic assumption.
Exactly.
So you have 1% error. You have between 0.328 and 0.339. So 0.011 is your is an estimate of your experimental error.
Right. So for this value, you can say that I take this argument. As the inequality of the masses grows, then the lighter one has a growing probability. And then also the accuracy or the relative accuracy for the heavy ones is dropping a bit. So here the heavy one is found to have 3%, while it's predicted to have 2.2%. Okay, so I call it one absolute percent. It's maybe you can say that it's 50% relative percent off, but absolute percent. So it's still all within 1%. But as we go to higher inequality, the probabilities become very unequal, and then the theory doesn't hold very well, and it's also not expected to hold. Remember that we made here an assumption that we kind of averaged out the absorptivity. And actually, I have to admit that in hindsight, it's quite surprising, maybe, that absorptivity averages out in a similar way for all three bodies. So it's some function, which is a function of the outcome parameters, but yeah, so what we measure at the end is some kind of an average of it, and the average is roughly equal for all three bodies. This is what the results are teaching us. So so this assumption that it averages out appears to hold to a good approximation, but I do not expect it to hold precisely. The same way that the ergodic assumption, I do not expect to hold precisely because the system has a finite lifetime. Only a system with an infinite lifetime can explore all of phase space really equally, you see? If a system just goes inside the container 10 times and then bounces out, you don't expect it to really thermalize or ergodicize or chaoticize and become truly chaotic. So here, it appears to be a good approximation, at least at the 1% level. I agree. And who knows, maybe later the agreement can be shown to increase. So if this is your direction, it's definitely within the question. Right now, these are very nice results. So it's more, we are now working on other directions, but this is also an interesting future direction.
Okay, that actually leads to my second question.
Yes.
The ergodicity part. If I ask this, if I try to apply this to, say, the Sun, Earth, Moon system, or Sun, Earth, Jupiter system.
Yes.
What would my prediction be, and is it even relevant? How can I discuss, is the system ergodic or non-ergodic? Can I measure whether it will ever enter the ergodic stage, or if it's completely regular?
Good. So the first system of interest, the Sun, Earth, Moon, is not in a chaotic state. It's in a hierarchical state, and therefore it is regular, or at least nearly regular. Okay, so there you don't want to apply statistical tools and chaos, but you want to apply perturbation theory. Okay, you know roughly the orbits, and you can compute corrections to these orbits. So there you're very analytical, very perturbation theory, and you don't want to do statistics, but there you do have deterministic predictions. The same holds for two planets. You said Earth, Jupiter, Sun. Maybe for very, very long times, maybe it becomes unpredictable. But for all reasonable times, it will just be a slow drift of the planetary parameters of both parameters as a result of the mutual influence of the two planets on each other. Okay, so it would be very analytic, very perturbative, and not chaotic, not a question of statistical physics.
Which of there's no scale separation in distances between the Earth and Jupiter to the Sun.
Right. There we have something else. We have a mass hierarchy, that the Sun is much heavier than the other two. Also, Jupiter is quite heavier than the Earth. So this probably helps. But you're right, there is no hierarchy in distances, so it's not quite a hierarchical system. It's not a hierarchical system in distance, but there is a hierarchy in mass, which allows you to use perturbation theory still. Because you can count orders of mass over the mass of the sun. So this will be the small parameter for the perturbation theory. Okay.
Any other student questions? Or anyone else?
Or anybody.
Okay. If not, then one last question. In LIGO and gravitational waves, we often deal with two-body systems. But the main effect that adds complexity is there is a third variable. There are spins. And if the spins are not aligned, then the system can also exhibit precession. And now a question is, are these chaotic or ergodic methods appropriate, or is the system well ordered? And how to predict the final state from the initial conditions when precession can actually be substantive.
So the question is about a triple system of black holes?
No, double system of black holes, but
Yes.
they both have spin vectors.
Yes.
And the spin vectors cause, they basically cause your angular momentum, your orbital angular momentum to be non-conserved, because it can exchange with the spins.
Right. I think I understand. So it's not a question about the three-body problem, but it's by analogy, you go there to the problem of the two-body or two black holes in Einstein's gravity, which is more rich and has the conserved quantities are no longer conserved. The Newtonian conserved quantities, that's the word, are no longer conserved. And then I think the approach I would suggest would be to do perturbation theory, I think, rather than statistical physics. At least this is my first inclination, because at the Newtonian level, these quantities are conserved. Let's say the spin separately. And then you can say, what is the amount of non-conservation of spin? So suppose it comes from a spin-orbit coupling, the orbit of the motion coupled to the spin of the motion. And that will give you some kind of precession effect for the spin at lowest order. And this is indeed done. There you have, at least in some regions, you have a perturbation theory, namely either post-Newtonian or extreme mass ratio. So in those cases, you can do some kind of perturbation theory and compute analytic corrections. Of course, in the relativistic regime with relativistic velocities, you have no replacement for a full simulation. So I don't know if I would call it chaotic, but I would call it outside of perturbation theory. So finally, when they're nearby, I don't think you can do compute corrections, because the precession will be fast and not small. And then you really have to do the full GR simulation. So I wouldn't call it statistical, I would call it, because I don't know that there is chaos there, but you really need to account for all the infinity of degrees of freedom. You have to account for the gravitational field all over space, right? You can't just simplify it to kind of a Newtonian model of point particles moving. Yeah, but all these things have some analogies and they echo each other. So I understand where your question is coming.
Thank you.
Okay.
Any other questions? If not, let's thank Barak again.
Okay, thank you. And
You're
thank
Thank
you
you.
for the attention.
And,